This is Module 14, Lecture Notes 27. Today we're going to be talking about reaction kinetics. And remember the word kinetic. We talked about kinetic and potential energy several units ago. Remember that kinetic energy refers to motion. Okay, so today we're going to be talking about the study of how fast a reaction goes towards the products. Okay, and we're going to study that by looking at the reaction rate. Here you have an equation for reaction rate. Okay, R stands for the reaction rate. And we're saying that the reaction rate is equal to the change in concentration of the product over the change in time, which is also equal to the negative change in the concentration of your reactants over time. So think about it this way. You start with some reactants in your reaction, okay? They're on the left side of your equation. And over time, they're reacting together and proceeding toward a finished product. And the reaction rate is the study of how fast or how slow that process happens. Okay, so in this reaction equation here, I just want you to note that this is the change in time. Okay, remember delta means change. And then also circle this negative sign here so you don't miss it. And then lastly, I want you to write that these brackets around the product and the reactant stand for concentration. Okay, so before we actually calculate the reaction rate in some specific reactions, let's talk about some factors that might affect the speed or the kinetics of a chemical reaction, okay? And these three factors you definitely need to know and be very familiar with. Okay, so first let's talk about temperature. And I think as a visual, we're going to go back to looking at my particles or my beads in a container. Remember several units ago when I simulated temperature by speed of how fast I was shaking this. Okay, so in order for a reaction to happen, the chemicals have to collide with each other. Okay, remember collisions are so important in chemistry. When you have more collisions, the rate of reaction is going to be faster because the particles are hitting each other more often. So let's talk about temperature. If my particles are at room temperature and they're colliding with one another, they're reacting. But what happens to the reaction rate if I increase the temperature? Are they colliding more often? Yes, then that means the reaction rate is going to increase. So in this first box here, I want you to write that increase temperature increases the reaction rate. So as temperature goes up, reaction rate goes up, because the molecules are moving faster and they're going to hit each other more often. You can even write a note here that increased temperature means that they're moving faster. Okay, and just keep that visual in your mind. Increased temperature, increased reaction rate. Okay, next let's talk about concentration. I think the best way to simulate concentration with our visual is for me to add more particles to our container. Okay, so if I add more of these, are they going to be hitting each other more often or less often? Well, of course, there's more of them, so they're probably going to bump into each other more often. Okay, so we can say that increased concentration increases the reaction rate. Why? Go back to collisions, because there's more reactant molecules colliding with each other. Okay, and then the last one we want to look at is surface area. So I'm going to say that as we increase surface area, we're going to increase reaction rate because the molecules can more easily mingle with other molecules. So you're going to get a chance to explore all of these in your lab activity. But for this last one, I'm going to draw a picture so that we can visualize this. If I put a whole tablet of something into my reaction versus little pieces of something into my reaction, which one has the larger surface area? Okay, this one has a larger surface area because there are more places where the molecules can be reacted. Okay, you might want to draw that with an arrow. Okay, here's my reactant, and I have some solution that's coming in and trying to react with it. Well, with a big tablet, it may only be able to come at that tablet from the exposed sides. But if I were to crush that tablet up into a bunch of little pieces, now my reactants can get in between one another and a lot more collisions can take place. Okay, so this last one you will best see in the lab. However, what I'm trying to show you here in the picture is that a larger surface area, meaning smaller pieces, will mean an increased reaction. All right, before we move on to some specific examples, I want you to stop and think about this question to see if you're really understanding how these factors affect the collisions, which in turn affect the rate of reaction. So let's say that we have two containers and they're filled with the same amount of nitrogen and hydrogen gases. The first container is slightly larger than the second container. In which container will the reaction be the fastest? Go ahead and pause this and jot down an answer, and then come back and see if your thinking was correct. Okay, remember reaction rate needs to go back to the theory of collisions. In which one of these two containers is it more likely that the particles will bump into each other? In the smaller one, where there's less room, it is more likely that the particles will collide with one another. Okay, so you can answer this by just saying the smaller one. And I would just write more chance of collisions. Okay, you could even draw yourself a little picture to remember. The smaller container versus the larger one when you're thinking about this concept. Okay, down here at the bottom of your paper, we're going to look at how reaction rate, or R, is calculated. And this is called the rate equation. So here I have a generic reaction. Let's say we have A added to B, and we're making two products, C and D. Okay, the rate of this reaction could be written like this. The rate is equal to K times the concentration of reactant A to the X times the concentration of reactant B to the Y. So let's look down here and kind of define what some of these new things are in the equation. Okay, like we said, little brackets around something represent concentration. So these are just the concentrations of A and B. K, little k, is the rate constant. Okay, and remember, constant is something that does not change. X is the order of reactant A, and Y is the order of reactant B. Okay? And adding X and Y together gives you the overall order of the whole reaction. Okay, this is a lot of new stuff that's probably not going to make a whole lot of sense until we jump into some problems and work through them slowly together. Now, as much as I don't like having to miss being in class with you guys, the one benefit to doing YouTube lectures is that you can listen to this as many times as you need to and watch me work through some example problems until it really clicks. So in this section that has lots of new things that could potentially be difficult for some of you, please play it back several times until you hopefully understand it. Okay, let's flip over to the other side. Okay, on the back side of your paper, we're going to work through some actual problems together to figure out the reaction rate of a specific equation. Remember, we said that reaction rate is especially affected by the concentration of the reactants, because the concentration of the reactants affects how many collisions they're going to have, and in turn, it's going to affect how fast the rate proceeds to the product. Okay, so up here at the top, I have that generic reaction rate equation from the other side with A's and B's as the reactants that are in the generic equation. But now we're going to look at some problems of actual reactions, okay? The thing that I like about this reaction rate part of the module is that the problems will always be exactly the same in their setup. So the two examples we're going to work through together in lecture, I have stepped through them the exact same way that you will step through them in your homework. And then that will be the same as you will step through them in a quiz or a test. So for those of you that like things very organized and like to follow things in a step-by-step manner, this should be easy for you once you get the hang of it. Okay, so I'm going to step you through two whole problems. And again, if you need to watch this multiple times, please do that. The first thing you're always going to do with reaction rate problems is you're going to take the generic rate equation and you're going to write a rate equation that applies to the problem that we're looking at. In this first one, we're looking at how nitrogen monoxide reacts with chlorine gas to make a product. So let's rewrite the basic rate equation. And instead of using A and B, we're going to use our two reactants. So I have rate equals the rate constant times the concentration of NO to the X, and we don't know what that is yet, times the concentration of chlorine gas to the Y. And we don't know what the Y is yet either. That's what we're going to do in step 2. Step 2 is the most important part of these problems, and it may take you a little bit to get the hang of it. Okay, we are trying to determine the order of X and Y, or basically we're trying to determine what exponent goes for X and what exponent goes for Y. There's only a couple choices to choose from with these problems, and I've written them at the bottom of the first page. So if you want to pause this and copy this down, it'll probably be very helpful to you as you're going through these problems. So the main orders that we're going to work with are 0, first, and second order. Okay? For a 0 order, what that means is that as the concentration of the reactants change, the rate isn't affected at all. It's like raising something to the 0 power. Anything to the 0 equals 1. So in a 0 order reaction, the rate is not affected by the concentration. In a first order reaction, the concentration and the rate are going to do the same thing. So if the concentration doubles, the rate is going to double also. That's a first order. And then a second order reaction means as you double the concentration, the rate actually quadruples. Okay, so it's like raising it to the 2nd power. So just keep those in mind as we go through these problems. All right, so we're going to look at the actual data from 3 different trials of this reaction in which the concentrations of the reactants change. So it's like they're experimenting with the concentrations to see how the rate here in the last column is affected. So if you have 2 different colors of highlighters or something, I think it might be helpful for you to see what's happening here. Step 2 says you're going to find 2 trials in which the concentration of one reactant didn't change. Okay, so do you see here how the concentration of chlorine gas didn't change? In trials 1 and 2, the concentration of chlorine gas is held constant. It's not changing. So that we can look at just how the concentration of nitrogen monoxide affects the reaction rate. And that's going to help us figure out what X is. We hold one of them constant, so we can see how this first concentration affects the reaction rate. Okay, so I'm just going to put my pen over that because we're holding those constant in trials 1 and 2. I want you to highlight trials 1 and 2 because we know in trials 1 and 2 chlorine isn't changing, and we're going to compare that to how the rate is affected. Okay, so in trials 1 and 2, the concentration of nitrogen monoxide started at 0.5 and it went to 1. It doubled. What happened to the reaction rate in those 2 trials? Did it stay the same? No. Did it double? You might have to do these on your calculator with decimals. If you're not sure what 0.019 doubled is, it's 0.038. So no, it didn't double. Did it quadruple? So we can multiply by 2 again. Yes, it quadrupled. Okay, so let me say that again. As the concentration of NO doubled, the reaction rate quadrupled. Go back to your choices. The concentration of the reactant doubled and the rate quadrupled. This is a second order reaction with respect to X. So you're going to put a 2 here. Okay. Now we need to figure out Y. So we're going to do that in the same way by finding 2 trials in which this reactant stays constant. Look at trials 2 and 3. NO remains constant in trials 2 and 3. So with your other color, you're going to highlight trials 2 and 3 this time. We're going to be comparing those while it remains constant. Okay, so let's do the same thing. Ask yourself, what happened to the concentration of Cl2? Well, it was 0.5 and it went to 1. That's doubling. And what does it do here? It started at 0.076 and it went to 0.152. So you might have to do that in your calculator. 0.076. Try doubling it. Oh, yes, 0.152. So the concentration doubled and the rate doubled. What order is that? When they do the same thing, concentration doubles and rate doubles, that is a first order reaction. So through these trials, we have figured out that this reaction is second order in respect to X and first order in respect to Y. The overall rate order, X plus Y, is 3. You just add it together. This will be the hardest step, this step 2. But once you get the hang of it, it will be pretty easy. You're either going to be putting zeros, ones, or twos in these boxes here. Rewrite the new rate equation. So that's asking you to copy down your rate equation from above. But now we know that X is 2 and Y is 1. Okay. Step 4, plug in the data from one of the trials to determine the value of K. So the rate constant is only figured out through experimentation. So we need to actually pick one of these trials and plug in the values and solve for K. So I'm just going to pick trial 1 and fill in those values. I'm going to say the rate is equal to K times NO squared times Cl2 to the first. That's what I have here. And the rate is going to be your reaction rate, 0.019. We don't know K. We do know the concentration of NO from trial 1 is 0.5. And the concentration of Cl2 from trial 1 is 0.5. And remember, your X and your Y are as you figured them out. So you need to solve for K here. So we're really saying 0.019 divided by 0.5 squared times 0.5 to the first. That's going to equal K. I move these things to the denominator to get K by itself. Okay, take a second to plug that in on your calculator and see what you get. Okay, remember when plugging values in on these blue calculators especially, you need to make sure you're telling it where you want your values, in the numerator or the denominator. So I'm going to plug in 0.019. I want to divide by 0.5 squared. I'm going to press equals, okay? But then I also need to put the other 0.5 in the denominator. So I'm going to divide by 0.5. You should get 0.152 for your value of K. If you don't, it's probably how you're putting it in the calculator. Last step is to put this all together. So we've figured out all these pieces to fill in of this generic rate equation, and now we're ready to write the actual rate equation. So we're going to say rate equals 0.152, because we figured out what little k is, times the concentration of NO squared times the concentration of chlorine gas to the first. That is your final answer. Okay, I know that was a lot, but I promise as you do more of these, it's going to become easier and easier to do this step 2. You'll get the hang of it very quickly. All right, so we're looking at a new reaction this time. Same steps, different data, and a different reaction. This time we're looking at hydrogen gas reacting with oxygen gas to make water. And we want to know how the concentrations of these two gases affect the rate at which water's made. So we have 3 different trials with different reaction or different concentrations here and different rates that came out of our experiment. The first step is always to write your rate equation. Rate equals the rate constant times the concentration of your first reactant to the X times the concentration of your second reactant to the Y. Okay? The second step is where you need to examine the data given to you to figure out X and Y. Okay? If you're figuring out X, you need to find 2 trials in which your second reactant doesn't change so that we can hold it constant. And I see here that in trials 2 and 3, the concentration of oxygen is not changing. Okay, so let's look at trials 2 and 3. And we could even highlight those in pink. Okay, then you're going to ask yourself, what's happening to the concentration of hydrogen gas? Is it staying the same? Is it doubling? Is it quadrupling? Here you can see that it doubles. 0.25 doubles to 0.5. How does that affect the rate? Is it staying the same? Is it doubling? Is it quadrupling? If you want to do this in your calculator, you can. It looks to me like it's doubling, but to make sure, you can multiply by 2, and indeed, this is also doubled. Okay, so the reactant concentration doubled. It made the rate double. What order is that? This is a first order. When the concentration and the rate do the same thing, this is a first order in respect to X. Okay, now we need to figure out Y. So through that same process, you need to find 2 trials in which your first reactant isn't changing or in which it's constant. And it looks like in trials 1 and 2, the hydrogen gas is remaining constant. So let's highlight trials 1 and 2 in our other color. All right, so that one's constant now, and we're just focusing on trials 1 and 2. All right, so in trial 1 it was 0.25. What did it do in trial 2? It doubled. Okay, go to your rate and see what happened. It started as 0.0102 and it doubled as well. Remember, when the reaction concentration and the rate do the same thing, it's a first order reaction. So this is also going to be a 1. Okay, your overall rate order will be a 2 because 1 plus 1 is 2. You can even make yourself a note to know how you got it. We're going to write our new equation, which means we're just going to plug in what we know now. We know that X is 1 and Y is 1. Okay, I want you to pause this video and see if you can do steps 4 and 5 on your own. You're going to plug in data from one of the trials to figure out K, and then you're going to write your whole reaction. Let's see how you do. Okay, in step 4, I just took the data from trial 1. I said that the rate, 0.0102, is equal to K, which we don't know, times the concentration of hydrogen gas to the first, times the concentration of oxygen gas to the first. And then I solved this for K by moving these 2 concentrations to the denominator. Remember to be careful with how you're putting this in your calculator. K should equal 0.1632. And then to finish out the entire problem, you're putting it all together. your reaction rate is equal to your rate constant times the concentration of hydrogen to the first times the concentration of oxygen to the first. You've written an entire reaction rate. So I know that's a lot. Hopefully as you're working through your homework, you'll see that the problems flow through in the same order. Please come back to this and play it again if you need to watch specifically how I figure out the rate order in these steps. Thanks guys for listening.